This is Chapter 14, Just-in-Time and Lean Operations. So lean operation is a flexible system that uses less resources than a traditional system. So you tend to have greater productivity, lower cost, shorter cycle times, and higher quality. Just-in-time is really a highly coordinated processing system in which goods are moved through the system or services performed just as they are needed. So here's some characteristics of lean systems: waste reduction, continuous improvement, the use of teams, work cells, visual controls, high quality, minimal inventory, output only matched to demand, quick changeover, small lot sizes, and a lean culture. So there's 5 principles that embody the lean systems. First is to identify customer values. You focus on the processes that create value. You eliminate waste to create flow, produce only according to customer demand, and you strive for perfection. So there's some benefits and some risk of lean system. So the benefits are reduced waste, lower cost, increased quality, reduced cycle time, increased flexibility, and increased productivity. But the risks, one of the risks is you really increase the stress on workers. You have fewer resources when you have problems, and a supply chain disruption of any kind can just halt your operation. So lean operations started in the mid 1900s. It was known as JIT, just in time. It was developed at Toyota, and the focus was on eliminating all waste from every aspect of the process. So waste is viewed as anything that interferes with or does not add value to the process of producing automobiles. So the ultimate goal is to have a balanced system. So you want to achieve smooth, rapid flow of materials or work through the system. So there's some supporting goals. So you want to eliminate disruptions, make the system flexible, and eliminate waste, especially excess inventory. So there's 8 sources of waste. First is excess inventory, 2 is overproduction, 3 waiting time, 4 unnecessary transporting, 5 is processing waste, 6 is inefficient work methods, 7 is product defects, and the last one is underused people. So Kaizen, this Kaizen is actually the Japanese word for improvement, but it's a philosophy for attacking waste. And it's based on these ideas. First, waste is the enemy, and eliminate waste. To eliminate it, you really have to get your hands dirty. And then the second thing is improvement is done gradually and continuously. So the goal is not to have big improvements that you do just every once in a while. You want to continually and gradually improve. The third is everyone is involved. And then the fourth, Kaizen, is built on a cheap strategy. There's all kinds of consultants that want to charge all kinds of money to do Kaizen, but it really doesn't require that much money or a bunch of consultants. It can be applied everywhere, and then it's supported by a visual system. It's real easy to see just by looking to see if it's working or not. It focuses attention where value is created. It's process oriented. And it stresses the main effort for improvement that should come from new thinking and a new work style. And the essence of organizational learning is to learn while doing. So now we're going to talk about some of the building blocks. So one of the building blocks is product design. So there's 4 elements that are important for lean systems. One is standard parts. The second is modular design. The third is highly capable systems with quality built in. And the last is concurrent engineering. So another building block is process design. So small lot sizes. So in the lean philosophy, the ideal lot size is 1. So one of the benefits of a small lot size is you reduce in-process inventory. That means you have lower carrying costs and less storage space is necessary. And then another advantage is inspection and rework costs are less when you do have problems with quality. If you have a line of 10 people or 10 workstations, and each of those are doing a lot size of 1, and you find a problem at the end, then you only have to rework 10 items because there's 10 items. But if each of those 10 stations had, say, 10 items or a lot size of 10, now instead of having 10 things you have to fix when you discover it at the end, you would have 100. So 10 for each workstation times 10, that would be 100. Inspection, okay, and then the next one permits greater flexibility in scheduling. So you can change easier when there's not this big pile of inventory in the middle. You have less inventory to work off before implementing an improvement. So let's say that you found a problem and you want to implement an improvement. Now, once again, you have 10 instead of 100 in that example that you have to work off. Increase visibility of problems. So if the 5th person or the 5th station in a row is constantly behind, if there's a batch before and after that person or station, you may not see that. But if everybody's waiting for station number 5 all the time, it becomes instantly visible, and now you can focus on station number 5 and make it faster, make it more efficient. And then it's increased ease of balancing operations. The same way, if you see maybe station 2 and 3 could be combined into a single station, and you take that extra person and put them on station 5, it's a lot easier to see when that happens. Process design, the setup time reduction. So small lot sizes and changing production mixes require frequent setups. Unless there's a quick, relatively inexpensive, they can be prohibitive. So there's something called a single-minute exchange of die. So a die is something that's used as part of the production of a specific part. And so the goal of a single-minute exchange of die is to be able to change from one kind of part to a different kind of part in a minute. And it's really a system for reducing changeover time. So group technology may be used to reduce setup time by capitalizing on similarities in recurring operations. The manufacturing cells. So one of the characteristics of lean production systems is multiple manufacturing cells. So the benefit includes reduced changeover time, high equipment utilization, and really the ease of cross-training workers. Another piece is quality improvement. Quality defects during the process can disrupt the orderly flow of work. So automation can be used for either the automatic detection of defects during production. So there's two ways to do this. One is for detecting defects when they occur. Another is for stopping production to correct the cause of the defect. Work flexibility. So here's some things you can do to increase flexibility. So the first is reduce downtime during changeovers by reducing changeover time. The second is to use preventative maintenance on key equipment to reduce breakdowns and downtime. The third is cross-training workers so that they can help when bottlenecks occur or other workers are absent. Another is to use many small units of capacity. So many small units make it easier to shift capacity temporarily to add or subtract capacity. Another is offline buffers. So you store infrequently used safety stock away from the production area. So in other words, if there is some kind of a safety stock or buffer, you go ahead and put that far away so that way you're not just constantly using it. And then another is to have reserve capacity for important customers. One of your important customers comes in with an urgent order. If you have that reserve capacity, it's like, okay, use the reserve capacity. A balanced system. So there's something called takt time, and this is really the cycle time needed to match customer demand for final product. So it's sometimes referred to as the heartbeat of the system. So takt time is often set for shift work. So you determine the net available time per shift. If there's more than one per shift per day, you multiply that by the number of shifts, and you compute the takt time by dividing the net available time by the demand. So this is very similar to what we did in the early sessions, where you just say, I need 10 widgets a day, and it's 10 hours a day of work. So the takt time is 10 divided by 10 is 1 hour. So every hour I have to get a system through. So that's your takt time, that's your heartbeat. If you have 100 systems in 10 hours, then your takt time would be, one every 6 minutes, 10 an hour, or one every 6 minutes. So you just take the total divided by the time, and that's your takt time. So now you know that if you are a person in the line creating this and your takt time is 6 minutes, that means you have 6 minutes to do this job, and you should be every 6 minutes getting one done. So the other is this inventory storage. So the goal is to minimize your inventory, and so what inventory tends to do, it tends to cover up your problems, and partially because they're not obvious, and partially because the inventory makes it less serious. So here's an example. So this is trying to say this is your inventory and here's your problems. Sort of your rocks, that this boat could get stuck on the rocks. So now you lower the inventory and suddenly these rocks are visible. So now you know what problems to work on. We got to remove this rock, remove this rock, remove this rock, remove this rock, and now you can function with that much inventory and you're not hitting the rocks. So it's an analogy, um, but the bottom line is, you want to be focusing on problems, getting better, getting more efficient, and eliminating that inventory it creates an incentive to eliminate those problems. Fail-safe method. So if you build safeguards into the process to eliminate potential errors or potential problems. So here's some examples that we see every day. So one of them is circuit breakers. In your house, you try to plug something in or too many things into an outlet. Without circuit breakers, what would happen would be the wires in your wall would overheat and could cause a fire and burn your house down. With a circuit breaker, the idea is that the circuit breaker overheats and trips, and now you know that you have too much. Seatbelt fastener warnings. So you forget to put your seatbelt on, you're driving down the road, and depending on your car, it's dinging, it's buzzing, or if you have a really fancy car, it may be talking to you. Fasten your seatbelt. ATMs that signal if the card is left in a machine. They're getting actually smarter. I went, they got these little chips now in there where you plug the card in and you have to leave the card there. Well, I went to an ATM and I plugged the card in and it actually sucked the card inside. No, it didn't suck the card inside, but it says leave your card there. And then, I asked for cash, and the money wasn't coming out. And then on the screen it said, take out your card. So you pull out the card, and as soon as I pulled out the card, the box opened up to give me my money, and it started dinging at me. They figured I wouldn't forget the money. Now, I'm not quite that good. I was at Walmart doing the self-checkout. And I asked for cash back. Well, I'm at this self-checkout, right? So, I pull my card out, I grab my bags, and I'm walking away from the machine, and then the machine is talking to me. I'm probably 10 feet away, and it says, please remove your cash. It's like, oops. And I turned around and went back. Fortunately, it was still there. I grabbed my $40. But fail-safe methods, designing parts that can be assembled in the correct position. So when you design this, you could put little things in so that you cannot put it in backwards. So those are examples of fail-safe methods. Personnel and organizational building blocks. So there's 5 organizational personnel elements that are important for lean systems. Number 1 is to understand that workers are assets. They're important, you take care of them. The second is cross-train workers. So you get people to know how to do other people's job. Continuous improvement, always making it better. Cost accounting, so you're keeping track of how much each little piece of a product costs you. And then leadership and project management. You're managing the projects, but you're also providing leadership and saying, this lean is important to us, we're going to do it. Okay, so now we're going to talk about manufacturing planning and control. MPC are the initials. So the first thing is load leveling. So you want to achieve stable, sort of a daily mix of schedules where you're leveling the capacity. So there's 3 issues that need to be resolved. So what's the appropriate product sequence to use? How many times should the sequence be repeated daily? And how many units of each model should be reproduced in each cycle? So there's a couple of options here. There's pull systems and push systems. So a push system is work is pushed to the next station as it's completed. A pull station, workstation pulls output from the preceding workstation as it's needed. So the output of the final operation is pulled by the customer demand or the master schedule. So pull systems are not appropriate for all operations. If you have large variations in volume, product mix, or product design, it will undermine the system. So there's a pull system. I mean, you think of it as the inventory being pushed through the system or pulled through the system. Visual systems. So Kanban is it's a card or a device that communicates demand for work or materials from the preceding station. So Kanban is a Japanese word for signal or visible record. An example, my wife worked at the hospital and they implemented Kanban on their inventory. And what it was is they actually had a card. So let's say you have a stack of 100 items and your reorder point is at 30 items. So the stack of 100 items, at 30 items, there's actually a card with the order information in the stack. So you're going through the stack, you're pulling, pull. You get to that 30 when it's the reorder time. There's actually a card that says reorder. And it has all the information. You take that card, you reorder, and then when the new inventory comes back, you reinsert that card at item 30. Another way that I do it is in my groceries and in my cans in the cupboard. So what I do is I have different kinds of things, and some things I have 3 cans of it, some things I have 6 cans of it, some things I have 12 cans of it. And I can go look at a glance and see, I need 2 cans of green beans, I need 3 cans of chili, I need 4 cans of corn, just by looking at it, because when my inventory is full, it looks full. So then the next thing is this paperless production control system. Another is the authority to pull or produce comes from a downstream process. You don't create it until it's asked for. So there's 2 types of Kanban. There's production Kanban, which signals the need to produce parts, and then there's conveyance Kanban, which is the need to deliver parts to the next work center. The next is limited work in process. So one of the benefits of lower work in process is you have lower carrying cost, increased flexibility, it aids scheduling, it saves costs of scrap and rework if the design changes, and lower cycle time variability. Another concept is close vendor relationships. So lean systems typically have close relationships with vendors. They are expected to provide frequent, small deliveries of high quality items. So a key feature of lean systems is really a small number of suppliers used. Reduced transaction processing. So it really seeks to reduce the cost of the hidden factory. So there's stuff that's visible, and then there's the invisible or the hidden factory. Logistical transactions, balancing transactions, quality transactions, change transactions. So all of those things are things that may be invisible in the production process, but each of them costs something. Okay, now we're going to talk about lean tools, and there's something called value stream mapping. So value stream mapping is simply a visual tool that systematically examines the flow of materials and information. And its purpose is to identify waste and opportunities for improvement. So here's some of the data that you collect: times, distance traveled, mistake, inefficient work methods, waiting times, and information flows. Okay, so there's something called 5W2H. So this is one of the tools. It's the 5W. It's a way of asking questions. So the 5 W's are what, why, where, when, who, and the 2 H's is how and how much. So you just go through, and every step in the process you say, what is this step for? Why are we doing this step? Where does this step occur? When does this step occur? Who does this step? How do you do the step? And how much do you need? And sometimes you get to the end of asking those questions, and it's like, well, why can't we just eliminate this step? And that's where you get non-value added steps, that you can find those and eliminate some of those. And then there's Lean and Six Sigma. So a lot of times you'll hear the term Lean Six Sigma. It's actually two separate pieces, Lean and Six Sigma. They're complementary approaches to process improvement. So Lean focuses on eliminating non-value added activity and maximize process velocity. Six Sigma seeks to eliminate process variation. So together, the two approaches achieve process flow and quality. If you focus only on Lean Six Sigma, your flow will slow down. If you focus only on Lean, your quality could drop. So transitioning to a Lean system, you have to make sure that top management is committed and they know what's required. You have to decide which parts need the most effort to convert. You have to obtain support and cooperation from workers. And you begin by trying to reduce setup times while maintaining the current system. You gradually convert the operations. You begin at the end and work backwards. You convert suppliers to just-in-time, and be prepared for obstacles, because there will be obstacles. So here's some of the obstacles. Management not fully committed or not willing to devote the necessary resources. Workers and management may not be cooperative. It can be difficult to change the organizational culture to be consistent with the Lean philosophy, and your suppliers may resist too. So now we're going to talk about the supplement to Chapter 14, which is maintenance. So maintenance is all activities that maintain facilities and equipment in good working order so the system can perform as intended. So there's a couple of categories. One is sort of the buildings and the grounds. The second is equipment. So the goal is to keep the production system in good working order at minimal cost. So the reasons for wanting to keep the equipment and machines in good working condition, first is to avoid production or service disruptions, not add to production or service cost, maintain quality, and avoid missed delivery dates. So some of the consequences of breakdowns: your operations capacity is reduced and orders are delayed. There's no output, but overhead continues. So that really increases your cost per unit. There could be quality issues. When it breaks, you could lose a product. It could be damaged. And then safety. What if employees or customers are injured. So there's two maintenance options. One of them is reactive, which is breakdown maintenance. So this is, you wait until it breaks and then you fix it. And the second is proactive or preventive maintenance. And this is reducing breakdowns through the program of lubrication, adjustment, cleaning, inspection, replacement of worn parts. So I'll give you my example, which is I had this 2000 Honda Accord. And I knew the clutch was on the verge of going. You can feel it. It's like the clutch is almost ready to fail. I know that the timing belt needs to be changed. And I know that I don't want to, I want to just get, I wanted to get just a little bit more out of the car. So I intentionally took a reactive approach. And the reason I could do a reactive approach is because I also have an Excursion. The Excursion doesn't get good mileage, but I knew that I had a backup system. So for 6 months, I drove that car back and forth to work. And, you know, I babied the clutch. I didn't bother to change the oil because, you know, it's like I'm going to get rid of the car when it breaks anyway. It's so I did that, and I squeezed an extra 6 months out of the car, and it never left me high and dry. But that's reactive maintenance. Proactive is really, you know, proactive maintenance on that would be to go ahead and change the clutch, go ahead and change the timing belt, change the oil, and see how much more I can get out of the car. So here's, you know, the whole thing of maintenance cost. You know, what's the optimum? What's the cost of a breakdown? And what's the cost of preventive maintenance? And, you know, it's sort of when those two curves cross, it's sort of that minimum point, you know, where the sum total is minimum. So the goal of preventive maintenance is to reduce breakdown or failures. You know, and we talked about loss of output, idle workers, schedule disruption, injuries, damage to other equipment or facilities, repairs, inventories of spare parts, repair tools and equipment, repair specialists. So the maintenance schedule. So a preventative maintenance schedule is periodic. It's scheduled according to the availability of maintenance personnel and to avoid interference with operating schedules. Maintenance is scheduled using some combination of you know, planned inspection, calendar, a predetermined number of operating hours. So you know, so on a car, you change the oil. You know, it depends on the car. You know, the old way was every 3,000 miles or 6 months, or 3 months, whichever came first. You know, I bought a new RAV4, and that one is 5,000. Well, they actually, it's 10,000 miles. It uses synthetic oil. 10,000 miles, and I don't know. It's 12 months. We've put 30,000 miles on a RAV4 in less than a year. So I don't even know what the calendar passage time is. I just know every 5,000 miles I need to take it in, and every 10,000 they're changing the oil. Every 5,000 they're just rotating tires and checking the fluids and stuff. So the frequency. So you strike a balance between the cost of preventative maintenance, cost of a breakdown. And it's really a function of the frequency of breakdown, the cost of a breakdown, and cost of preventive maintenance. So here's an example. The frequency of a breakdown of machine per month is $1,000. The cost of preventative maintenance is $1,250 per month. If the preventative maintenance is performed, the probability a machine will break down is negligible. Should the manager use preventative maintenance, or would it be cheaper to repair the machine when it breaks down? So here, here's the number of breakdowns, the frequency of occurrence. So here's actually the math. Expected number of breakdowns, so it comes out to be 1.4. 1.4 times 1,000 minus 1,250 is $150. So the benefit of preventative maintenance in this particular example is $150. So here's another example. Suppose the average time for a breakdown is normally distributed with a mean of 3 weeks and standard deviation of 0.6 weeks. If the breakdown costs an average of $1,000 and preventative maintenance costs $250, what's the optimal maintenance interval? So preventative maintenance divided by breakdown cost, 250 divided by 1,000, 0.25. Find the number of standard deviations from the mean represented by an area under the normal curve of 0.25. Use the table. It's minus 0.67. So use this value, so it's mean plus z times standard deviation equals 3 plus minus 0.6 times 0.6 equals 2.598 weeks. So even if you can't do the math, if you just understand, there's going to be someone who works for you that can do this math, and you just tell them, hey, calculate, based on these numbers, what is this? And they can calculate this for you. So another maintenance approach is called predictive maintenance. It's really an attempt to determine when best to perform preventative maintenance activities. So ideally, preventative maintenance would be performed just prior to a breakdown or failure, because it will result in the longest possible use of equipment without a breakdown. And then another approach is total productive maintenance. So this is a just-in-time approach where workers perform preventative maintenance on the machines they operate. So maintenance problems are sometimes designed into the systems. Poor design, a designer have they have other aspects of the design have greater importance. Cost or appearance is more important than maintenance activities. My brother-in-law had a BMW, and he went in there to try to change his own oil, and it's like he had to disassemble the car to get the there was like a panel underneath that you have to take off to get to the oil canister, and to change the filter and everything. And it's like, this is too hard. That's an example where the aerodynamics, they actually had a plate underneath, and it was they put aerodynamics over the cost of changing the oil. Breakdown problems. So there's different approaches that you can use with dealing with breakdowns. So one is to use a standby or backup equipment. So this is what I was doing. I had my Excursion as my backup equipment and my Honda on the verge of breaking. Inventories of spare parts are maintained. You can have the parts there ready so that if it breaks, you just slap it in and you're done. We already talked about the operators doing at least the minor repairs. And you can also have the repair people well trained and readily available to diagnose correct problems. Replacement. So when breakdowns become frequent or costly, what is the cost of replacement compared to continued maintenance? So predicting breakdowns, technological change, system disruptions, training employees to use new equipment, forecast the demand. So, so this is another example. The Honda used to be our main car, and as its clutch was breaking or going, we went ahead and bought a new RAV4. I decided to keep the Honda around because it wasn't that expensive, but then I decided to get rid of it after that. So then the Pareto phenomena and maintenance. So we talked about the Pareto effect, which is the 80-20 rule. So 80% of your problems comes from 20% of the sources. So the breakdown programs are most effective when they take into account the degree of importance of a piece of equipment in the operating system and the ability of the system to do without it for a period of time. So a few pieces of equipment, so 20% of your equipment are do 80% of the work. So those few pieces of equipment are extremely important. So those pieces of equipment you might do preventative maintenance on, where the other 80% of the equipment you might do reactive maintenance on those. Some require moderate effort or expense, and some will justify minimal effort or expense. So summary. So we talked about the building blocks. There's product design, process design, personal organizational elements, manufacturing, planning, and control. There's the value stream mapping, 5W2H. What, why, where, when, how, who, how, and how much. Lean and Six Sigma, transition to a lean system, and the maintenance supplement.